Everybody, my name is Dario Sanalitro and today I'm going to present our collaborative work between University of Catania and University of San Diego on visual feedback BCI systems for aerial vehicles. My first question for you is, what if we could utilize drones as an extension of our bodies? Imagine you would like to have a glass of water. If it's close to you, then it's easy, you drink it. But what if the juice is far from you and where you are? In this specific case, one solution is to approach the juice and drink it. But another solution could be using a robot to bring the juice to you. And for example, as it's shown in the small video. And the same applies to a tool, for example, that is out of the human reach, as for example you can see in this video, and instead of taking a ladder, a drone could perform the task for us. Now, question number 2. What if we could send these commands directly with our brains? These companies are all examples of this by providing humans with new capabilities and possibilities. And for example, they are working on invasive and non-invasive devices. Particularly, the question is, what kind of challenges are these companies encountering in this field? Human intention decoding, meaning translating brain signals into machine commands, is the first challenge. The second one is to provide consistent and reliable commands. And another one is actively providing information back to the machines. The focus of this work is on feedback provisioning. In particular, according to the Brain-Computer Interfaces Handbook, there are primarily 2 methods employed in the current state of the art to provide input to the machine: steady-state evoked potentials and event-related potential. Among event-related potential, the P300 is an ERP component that shows a maximum positive peak about 300 milliseconds after a stimulus onset. Another one is the error-related negativity, which is an event-related potential present in EEG signals when users are aware of an erroneous behavior. Specifically, it consists of a negative voltage deflection over frontocentral regions, followed by a positive voltage increase over parietal regions between 15 and 500 milliseconds after the commission of a speeded motor response. Error-related negativity has already been used in some application. For example, in this work, the authors used error-related negativity to correct robot mistakes inserting objects into boxes. As you can see, when the robot makes an error in the task execution, the error-related negativity response offers feedback to the robot, helping it to correct its mistakes. In this specific context, our contributions are first related to this scenario. Error-related negativity has not been applied to aerial vehicles, and such a scenario could have the challenges of faster movements, for example, and greater noise compared to ground-based manipulators. In addition, the methodology to isolate error-related negativity response, namely independent component analysis, have never been used in robotics online, and specifically with aerial vehicles. So our goal is to develop a system that enables active control by allowing users to imagine a movement and provide feedback at the same time in response to a speeded motor response. Focusing on providing feedback, the protocol considers And aerial vehicles that flies from a point A to a point B several times. And at a certain point, the aerial vehicle goes to a wrong waypoint that the user previously instructed considers wrong. Such a wrong waypoint should then elicit an error-related negativity, and in our specific case, 20 waypoints per trial were given, and 42% of them were incorrect. So this video shows the protocol and the experiment in action, where you can see the robot navigating from point A to point B and sometimes reaching wrong waypoints. Regarding the experimental setup, brain signals have been recorded through Biosemi Active 2, a commercial cap that contains 64 electrodes, and ROS Neuro, an open source neurorobotic middleware, has been used for signal recording. To remove artifacts and unwanted noise, a set of filters, including the artifact subspace reconstruction, has been used. To extract the features, meaning to get useful information from the data, we use independent component analysis, a recursive algorithm, which is largely employed to separate independent sources linearly mixed in several sensors. In our specific case, error-related negativity needed to be separated from other sources. After making the error-related negativity emerge from the data, we performed linear discriminant analysis, which is a standard algorithm which helps in identifying two or more classes. In particular, it helps in determining the presence or absence of the error-related negativity based on specific features, namely mean, standard deviation, skewness, kurtosis, and slope sign change. Two phases can be considered in our scenario. An offline stage, which could also be called the calibration stage, related to the person using the system, and an online phase. Our preliminary results are related to the calibration stage. In particular, they involve the computation of the ICA decomposition, where we look at the scalp map to see activities in the frontal cortex, the power spectrum to look for a frequency deflection at n Hz typical of an error-related negativity, and the alternation of a negative and positive voltage in time domain. So this slide shows all these features for the epochs related to the error-related negativity in one of the performed experiments. After this stage, we perform the offline model creation. In particular, we considered 280 trials over 10 data sets related to a single person by considering 2 ICA components per experiment. 512 samples were considered for the time window, and 70% of the data set was used for the training phase, and 30% for the test phase. And accuracy of 85% was obtained in identifying the error-related negativity. As future work, we aim to develop a real-world scenario in which not only the electroencephalography signals are recorded, but the robot also runs in combination with the human. Moreover, in terms of methodology, an online analysis should be performed, and therefore the ICA decomposition should be validated online. By combining these two things, the offline calibration will be complemented with a pipeline that runs online and that allows humans to provide feedback in real time to the robots. As I told, thank you for listening, and just some acknowledgement. So these are the projects that are funding this